Hi, I'm David and welcome to What Circuit. For this video we're going to take a look at a power meter, specifically the HAMEG HM8115-2. So this is a nice power meter. It's 0 to 500 volts, 0 to 16 amps, and yeah, we're just going to take a quick scan through some of the functionality. Recently Star's been finishing off his master's dissertation, and for that he's been using a power meter pretty much continuously for about the last 6 to 8 months. And becoming slightly dissatisfied with the model that he was given to use. So we started having a look around some of the other models on the market, and this one rather caught our eye and actually looked like a really nice high specification for the money. So we got hot wild one of these from HAMEG, and we're going to have a quick play with it. So of course, why do you actually need a power meter? And broadly speaking, we can break down sort of applications into either DC and AC applications. So first of all, let's have a look at DC applications. So a very basic circuit, we've got some form of DC power supply here, connected to a load. What do we actually need to measure the power? First of all, we need to measure the voltage across the load. And then we need to measure the current going through the load. Now it's this sort of thing, so we've got 2 meters here, typically 2 multimeters. This is, very often cited as the reason why you want to have multiple multimeters around. So we've got it here, so to get the power out we have to do is multiply the current by the voltage. Because what we've got here is a really simple example. We've got an absolutely constant resistance for our load here. In real life, that's really, that's not likely to happen. You might be looking at, say, a microcontroller circuit, where you're going to be switching various bits of circuitry on and off. You're going to look at pulse loads, something like that. So an application, for a certain DC application, your voltage is probably going to be constant, but your current probably isn't. So then you may be looking at getting a current probe and then putting the output across your into your oscilloscope, or maybe looking at putting a resistor in the line. Then you've got issues with burden voltage. Much easier, you can just take one instrument, drop it in, measure it out. So typically here, constant voltage. Let's say our current looks a bit more interesting. We're going to have something like that. So our power out, going to look something like that. Now the nice thing about the HAMEG power meter is it does all of this for you, and it's going to give you the output in one of 2 ways. It's either going to output it on the front panel, which is lovely if you look at a more sort of steady state example, or it's going to throw those measurements out to PC, which is nice if you want to do sort of long-term logging or looking at slower phenomena. And it also throws an instantaneous power output out of a BNC connector on the front, which you can connect up to a scope and get an idea of what your power waveform looks like. So all of these works really nicely. So the next main application is actually with an AC voltage supply. So here we've got another basic circuit drawn up. We've got some form of AC voltage supply. Again, we're measuring the current and the voltage, and let's just start off with a resistive load. So we're dissipating power in this resistor, in our load. We've got an AC voltage, and we've got an AC current. You notice, any fault in the drawing is down to me, but so they should be completely in phase, and the power is just going to look like a sine wave. So this is a nice basic system. So let's say you're doing this with multimeters. In this case, you could just take the RMS current, multiply it by the RMS voltage, and you get the RMS power output. Nice and easy. Okay, so in that case, why do we need a power meter? Well, let's say a load gets a bit more interesting or a bit more applicable to real life. Across this resistance here, you might find you've got a bit of inductance, or you might have a bit of capacitance. Now what is that going to do to our current waveform? Our voltage waveform still looks about the same, but our current, just taking again a simple example, our current is going to what's called phase shift. So maybe our current is just going to move off a little bit. So here it's just moved to the right a little bit, or maybe it's going to move to the left a little bit. Now the problem is, if your current waveform is doing that, and you take a nice simple reading of RMS current multiplied by RMS voltage, your power doesn't actually match up to what the actual power is anymore. What you need to do is allow for this, so we'd have a measurement called power factor, which, again, in a simple example where it's all sine waves, is going to be equal to the cosine of the phase angle difference between the voltage and current waves. And then your power is equal to current multiplied by voltage multiplied by cosine of the phase difference. But again, you can go to even more complex waveforms than this, where suddenly your current waveform isn't looking like a sine wave anymore. How do you then measure power accurately? For this is when you really need a power meter. Right, so a bit more of a real world example then. What we've got drawn up here is just a very crude power supply. So we've got AC voltage in, presumably from the main supply, putting it through a transformer, through a bridge rectifier, so that's going to give us a DC voltage out at a lower voltage, and then we just smooth that voltage off with a capacitor, and we've got some form of load out here. So the voltage out of the bridge rectifier, if we didn't have the rest of it attached, is going to look something like that. So we've got what's called a fully rectified AC waveform. But we've got the capacitor and load across here, so the actual voltage at that point is going to follow that, and then it's going to drop down. So what we've got there, at this point here, the voltage coming out of the bridge rectifier has got high enough so it's actually charging out the capacitor and running the load. It's charging out right until it hits the peak, but then as this voltage drops away, the capacitor is then actually starting to run the load. And drops away, the capacitor discharges until we hit the lower voltage, and the voltage from the bridge rectifier comes up again. So, interesting question then, what's the current waveform going to look like? When we hit this point here, we'll suddenly draw quite a lot of currents. Follow that down, out there, and then that voltage, or the current rather, is going to just die away, just like that. And then at this point here, now remember this is a rectified waveform, the current at this point isn't rectified, so it's going to drop down and then come away again. So running a typical linear power supply like this is actually what your current waveform is going to look like. And you can see that if you actually try to measure this in a multimeter or a standard current measuring device, your power readings are not going to be accurate at all. This is the kind of thing where a power meter really excels, and the HAMEG power meter is going to give you a spot on accurate power reading, even with waveforms like that. Right, so what we've got set up here is just a quick demo of the kind of thing you can use the power meter for. So we've got an AC application here. We've just been lazy and just hooked up the TV, going through the power meter. As if it's just broken out the cable, some 4mm shrouded plugs on there. So as you can see, power meters measuring voltage in, current being drawn, as it's in standby node, about 48 milliamps, not very much. And we've got real power just being shown up on here. So currently showing real power, we can iterate through, and we've got reactive power here, apparent power, and very small power factor. And one of the things I really quite like about this, we've got the monitor output here, BNC, got fed into the oscilloscope, and this is actually showing the power that's being drawn from the mains in real time. We've got this on 2 milliseconds per division, so we've got 10 divisions on here, 20 milliseconds or 50 Hz as we've got here in the UK. That's going to be about one period. Obviously we're seeing power being drawn, so as the voltage goes negative, current goes negative, and the power stays positive. So you can see you've got the power being drawn here. So let's try switching the TV on, see what happens. And see, just quickly auto ranges here. And it's really interesting, you can actually see all the switch mode power supplies starting up. You can see the way the current waveform changes. And it's auto ranged into new mode here. It's now drawing a bit more current, up to about 1/4 of an amp or so, or falling away a bit, 178 milliamps there. And our power factor's gone up quite nicely. It looks like we've actually got some power factor correction or something built into this. One thing to realise, because the power meter is so sensitive, if we actually just change the channel here, you can actually see the difference in power consumption. Let's just put it onto BBC News there. And see, this immediately comes right up. And you can start to see that waveform just open up a little bit there. So yeah, and obviously, you're not necessarily going to go around and monitor all your appliances, although we have, Sajal did do this for his station. But it just gives you an idea, if you're actually debugging stuff that you've designed and built yourself, really gives you a lot of insight into what it's working, especially here it's all working normally, but if you're looking at fault conditions, that sort of thing, and some of the EMC compliance stuff where you're looking at how well it's working in terms of injecting noise back into the mains, this gives you a lot of insight into what it's doing. So what we've got set up here is just a typical DC example. So we've got a bench power supply feeding through the power meter, and we're feeding this into a switch mode converter, which is just driving LED in constant current mode. Just got a Cree LED here, typical sort of lighting application sort of thing. So we've got the readouts on the front here. We can read off the voltage, we can read off the current, and we can read off the wattage. That's very useful. And in fact, if you look on the monitor out here, we've got flicked up to the scope. You can see it's actually, the way it draws power is very noisy. Because it's switching on and off, and for this particular converter it's switching on and off at variable frequency, which is why the waveform looks so very terrible. Let me just single shot this for a minute. So you can see here, you can actually see the switch mode power supply working here, switching on and off. This is running about sort of 200-300 kilohertz. Like I say, it's a variable frequency one, so it does change its frequency dynamically. And we can just see it drawing different amounts of current there. Nice thing is, because this power meter actually runs up to high frequencies, this wattage measurement here is actually going to be just about right. So yeah, it works really nicely for this sort of application. Very good for debugging, and very good for actually working out sort of long-term battery life issues, that sort of thing. Now, one of the reasons we actually asked to have this HAMEG bit of kit to review, because we've been using power meters a lot recently. In particular, Sajal's been investigating the feasibility of using what are called DC microgrids, so actually feeding DC electricity supply around a house. So as part of that, we've been looking, taking a lot of measurements, a lot of logging of various, household appliances, that sort of thing, and just looking if it's feasible. To do this, we actually borrowed a bit of kit. It's a GW Instec power meter. Don't know if you can read or not. It's a HM8115-2 power meter. So this is our, reference power meter. This is what we've been using a lot recently, and it's fairly good, but it definitely has a few bugs and bits where it doesn't work quite as well. So in this section, what we want to do is just do a quick comparison of the performance of this with the HAMEG. And what we've done here, we're feeding arbitrary waveform generator actually as a power source. We're feeding that into both the power meters, and we're feeding those out to a 1 kilo ohm quarter watt standard resistor. So we've got a plus minus 9 volt sine wave, feeding that into a 1k resistor. Obviously you can calculate the power. So you're expecting to see about, or 40.7 milliwatts is the expected power, and we confirm that using the oscilloscope, current clamp, etc. So, first off, let's do a one spot check on the accuracy. Let's see what the HAMEG reads as the power. Let's see what the GW Instec reads as power. So on the HAMEG, we can see down here we're getting between 40, just up to 42 there. 41, 42 milliwatts, that's pretty close. And let's just swap over the power meters here, and down to 40, so 40.7 milliwatts, that's pretty much spot on what we're seeing. So just connecting up the GW Instec here, we're seeing 39 milliwatts here. So not far off at all, but a little bit out. So, the other interesting thing is possibly a little bit of a simplification, but let's actually just try taking out the frequency of the source. And just to give us a number to compare, let's try finding the minus 3 dB point, or in other words, that's the point where the power read is going to be half the actual power. So as you increase the frequency, we're driving resistive load, the actual power dissipated and delivered by the source is going to stay the same. However, as the frequency response of these two power meters dies off, the red frequency, there and there, is going to drop. So obviously you're wondering, is this actually important? Generally mains frequencies are quite low, and yes, generally they are. Typically seeing 50 Hz in Europe areas, you're going to see 60 Hz more sort of US. One of the points at work, typically though, looking at aircraft, you see a lot of 400 Hz power supplies, and for that you really do want that bit of extra frequency range. Not only that, but also you want to be able to capture all the power generated by harmonics. And particularly, you're looking at sort of things like CE certification, that sort of thing. You're going up to quite high numbers of harmonics, up to sort of 15th harmonic or so, and that you start to actually get some fairly high frequencies you want to be able to see. And if the power meter can't read them, you're losing information and you're not getting quite the right result. So let's bump up frequency, let's see what happens. So minus 3 dB point for this, let's say it's at 20 milliwatts. So we're up to about 100 Hertz here, 2, 3, 400 Hertz. I'm not really seeing any drop off in frequency in power here. And we've hit a kilohertz. It's definitely seeing the power drop off now. But we are up at sort of 10, 11 kilohertz now. Oh, let's dial that back a fraction. They are around 20 milliwatts or so. And we're getting that around 13 kilohertz. So yeah, that's a pretty good frequency response. Drop that back to 50 Hertz, and we go back. Right, so now getting a reading out on the HAMEG. 3 dB point is going to be sort of, call it 20.5 milliwatts or so. We're not going to get any more actually on that, so call it 20 milliwatts. So unsurprisingly, up to a kilohertz there, we're not seeing any change at all. Now this is quite impressive. We're getting up to 7 kilohertz here, and we're really not seeing that number dropping at all. 20 kilohertz there. Let's start. There we are. Now we're starting to get a drop off here. We've already hit 50 kilohertz. And we're just around the minus 3 dB point there. That's around 130 kilohertz. So just taking those two numbers is a very slightly simplistic reading. We're getting around 10 times better frequency performance on the HAMEG scope. Very impressive indeed. So it just shows, a bit of good design there. Well designed front end. It really does make quite a lot of difference when you start hitting that those higher frequencies. So one of the major uses of power meters is actually connect up to PC or something like that. Two main uses of these are part of automatic test equipment, where you're going to have this part probably built into a rack, something like that, and you're testing products that go out. It's quite useful actually, just doing basically sandy checking. It picks up on a lot of faults, that sort of thing. The other one which we've come across a lot is actually doing logging over long periods of time. So let's say you've got a fridge freezer and you want to see what how much power it's drawing over a week. Just to get an idea of typical household consumption. It's very useful just to be able to hook it up to a PC quickly and easily. Again, what we're going to do, we're just going to compare it to the GW Instec, which we've been using so far, just to give you an idea of what's out there. The GW Instec has got a serial port on the back, which you can connect up to a PC. The HAMEG comes as standard with a fully opto-isolated serial port and a fully isolated USB port. Very nice options. So first of all, let's have a look at the GW Instec software and get an idea of what that does for us. So you've got the GW Instec software running up on the screen here. As you can see, it's a very basic bit of software and looks a bit amateurish really. Presumably being developed using some kind of National Instruments things. We've got a NI logo up here on the top, LabVIEW or something similar. What's this giving us? This is giving us all the readings that we get on the front panel of the unit. It updates about sort of once a second or so. We can also select the ranges manually, and it's got the basic bits just to communicate with it. It's a functional piece of software, but it really doesn't do anything beyond that. When we were doing logging, we had to write our own bit of software, and had to dive into all the commands, send the right commands to get all the data back we wanted. So it's a nice example bit of software, and it does a bit of basic functionality, but it's not really that useful for anything. So let's move across to the HAMEG one here. So immediate impressions, much more professional piece of software. You've got the usual interface bit here just to set up. So we're connecting it. It's actually a USB connection, but it's a virtual COM port. We've got all the readings that we would have off the front panel. If you notice, we actually get a little bit more accuracy on these readings. We've actually got an extra decimal place on each of these. Very nice. We can see what the range is, and see here it's set to auto ranging as well on all of these lot. We're actually running a DC load of this, so it won't do anything, but we can. So you can't get it set to watt. Let's say we set it to VA. Unsurprisingly, it's the same. VAR. Oh, of course, pulse DC load. I'll get something on there. And power factor of 1, unsurprisingly, as it's DC. Okay. One thing we really like on here, for a start, you can actually send raw commands over here. So when you're developing a bit of software, if you want to do something more custom, a bit more unusual, you can use this to actually do development. I believe, do show data traffic, it'll actually start to log. You can actually start to see what's going backwards and forwards here. There we are. What the answer is here. Yes, you can actually see the traffic going backwards and forwards. Right, and then one thing we really liked, logging. So loop time 1 second. You can actually get readings out a bit faster if you do it yourself, but yeah, that's what it comes up with. So it really is simple, just doing start here. See, we're reading voltage, current, and watts. Interesting little thing here, you can do rotational measurement. So you've got voltage, current are always red, and then we're reading watts as our additional category. We can then start to add additional bits to it, and it'll alternate between all the settings that you changed here. So new readings here are alternating between watts and power factor, and we can just add on. So now we've got watts, power factor, and VA, just rotating between all three of those. So yeah, pretty neat. It seems a slight shame you can't get all six readings out just in one line and do that once a second. I'll be surprised there's technical limitation, but yeah, this is a good way around. The software works very nicely. Oh, you can actually, just doing the rotational measurement here, you can actually watch the mode changing every time. So yeah, really nice bit of software, and also, given that this is a HAMEG bit of software, you know it's going to be updated for the latest version of Windows every time. This one, it's incredibly easy to download and install. Again, if you want to give it a go, you can just download it straight from the HAMEG website, and works absolutely beautifully first time. Yeah, so really nice bit of software, very high amount of functionality in there. So just to summarise our feelings on this then, we are really pleased with this power meter. The actual usability of this is absolutely brilliant. It's got a really bright, clear display, which is visible from quite a long way across the lab. Especially with some sort of power stuff we've been measuring, where you're measuring larger appliances and larger bits of kit. That's a really nice feature. Actually, using the front panel is very easy, very straightforward, which isn't saying a massive amount in the functionality. Also, when you have this hooked up to a PC, the actual software on the PC is very intuitive, very easy to use, and it's got all the functionality you want built into it. Stuff like the long-term logging, that kind of thing. We've had this hooked up to a PC, days at a time, logging away. It's run absolutely flawlessly. We've also tried hooking the serial data straight out to a microprocessor. That works nicely as well. So if you want to actually build it into part of automated test equipment, something like that, it's a very nice way of doing it. Yes, I know those sort of major factors for us in terms of actually using a power meter. As we've seen, it's really spot on accurate. The updating rate is quick, and actually one of the big things compared to on the GW Instep we actually compared, but compared to some of the other ones we looked at as well, the actual frequency response is very good indeed. You're looking at some of those higher harmonics. That really does improve the accuracy a lot, and actually gives you a lot more in terms of functionality. And some of the stuff certainly I get involved with at work, working on aircraft systems, running at 400 Hz. You really do need that good frequency response, otherwise you're just going to miss half the information. And during the teardown, we've had a look inside this. The build quality of it is absolutely excellent. very nicely made boards, well put together. You know, there's no cheaping out in terms of chips. They're all nice, solid manufacturers. Analog Devices, Fairchild, SD Micro, good people. We do have one slight issue with this. Let's take another bit of test equipment, like an oscilloscope here. Plonk it on the top. Classic stackable HAMEG system, works rather nicely. Let's turn it sideways. It's a very, very deep bit of kit. You know, in the end, it's a power meter. We're not expecting, you know, you're not expecting it to be the same depth as an oscilloscope with a modern TFT screen, something like that. But this is exceptionally deep. And let's just put it up on the bench for the minute, up on the shelf rather. So that's without a mains lead plugged into the back of it. In fact, and okay, you can get this a bit better with a 90-degree power lead, but I haven't got one to hand. It's a real shame to have it that deep, especially when, you know, there's a lot of empty space and it could actually be made a lot more compact. HAMEG, if you see this, it'd be lovely, you know, version 3 or something like that, if you could just shrink it a bit, just make it a bit more suitable for a sort of modern bench rather than something where you're having to have a giant deep CRT to get a suitable acceleration voltage on it. If it needs to be compatible with, you know, the standard sort of stackable bits, could we have a riser or something like that in the back that's just optional? But anyway, yeah, that's a pretty minor complaint considering. And especially a lot of the time, you know, power meter, you really actually do want it at the bottom of your bench. So yeah, this is a lovely, absolutely great bit of kit. We've done some serious use of this for several days, loads of different loads. You know, Sajada's used this for his dissertations. We've wrung a lot of use out of this, and it hasn't put a foot wrong at all. Very impressive bit of kit. So, I'd just like to say thanks to HAMEG for giving us a chance to review this. And if you like the video, please give us a thumbs up on YouTube. Thanks very much, and hope to see you again soon.